Now we're down to everyone's favorite, the analysis. We're going to take a look at how to walk from hypothesis to correct choice of test for basic hypothesis testing. To begin with, the fundamental units of statistical inference are the paired statistical hypotheses. Statistical hypotheses differ from just regular hypotheses in some important ways. For one, they come in pairs, with one hypothesis being what we would call the null, and the other being the alternate. The null position is that everything observed is due to random chance and there are no differences between groups. The alternate position is that the effect observed is real and not due to chance. They must be mutually exclusive. So let's take an example. We want to know if men and women have different outcome scores for rotator cuff surgery at 12 months. So we construct a null and alternate hypothesis. Our null is that men and women have the same outcomes on work scores 12 months post-rotator cuff surgery. The alternate is that men and women have different outcomes on work scores at 12 months post-rotator cuff surgery. Next, we want to ask ourselves some questions. What kind of data is your primary outcome? How many groups are you comparing? Do you have more than one independent variable? Are you comparing more than one measurement from a single subject? So for this question, our outcome is work score, which is continuous, numerical, and normally distributed. We've got two groups, males and females, only one independent variable, and no repeated measurements. The test of choice here is a two-tailed, unpaired t-test. We're going to tweak our previous example a bit. Check out the difference in wording of our hypotheses. Note that I've imposed a direction on the potential difference. So back to our questions, and the answers are all the same here, except that our test of choice is a one-tailed t-test. In brief, a two-tailed test allows detection of significant differences in either direction, but is a little less powerful to detect any given difference. A one-tailed test makes an assumption about direction and is more powerful to detect differences in that single direction, but it will miss differences in the other direction. This is a factor in choice of non-inferiority trials, since you only want to know about one direction. Because of the issues associated with one-tailed tests and the potential for abuse of the data, many statisticians recommend using the two-tailed approach for exploratory work. Tweaking our example again, this time we want to measure the overall impact of surgery on work scores. Note that I'm making no assumptions about improvement or worsening of scores. Answering the same questions, the main differences here are that there's only one group and that there's more than one measurement per patient. In other words, the data is paired and we've got a repeated measures design. The winning test here is then a two-tailed paired t-test. Moving to a slightly different example, let's say we want to find out if patients on anticoagulation wait longer for hip fracture surgery than those who aren't anticoagulated. In this instance, our null hypothesis is that patients on no anticoagulation, warfarin, or DOACs have the same wait times from diagnosis to surgery. This time, our outcome is time, which is also a continuous, assumed normal distribution variable. We have three groups though, control, warfarin, and DOAC. There's only one independent variable and no repeated measures. The winning test here is a one-way ANOVA because there's one independent variable but more than two groups. Now for a bit of complication. Let's say we're going to use cadaver elbows to study effects of loss of joint surface on joint stability. We're going to progressively remove joint surface while testing stability during the flexion arc with the arm in different positions. We want to see what factors will cause significant increase in angular displacement. Here, we have angular displacement as our outcome, which is still continuous, numerical, and normally distributed. There is one group, that being elbows. Our independent variables are now multiple: flexion angle, arm position, and bone resection. Since we're using the same elbows for each bone resection, this is also a repeated measures design. Our test of choice for this would be a three-way repeated measures analysis of variance. When you're doing ANOVA testing, there is a second step. All the ANOVA tells you is that there is a difference somewhere between something and something else. This is like the shell game. What happens next is a whole bunch of t-tests to find the difference. It's like turning over all the shells until you find the pearl. This is called post hoc testing. One more example. Let's say you wanted to know whether satisfaction is different between patients receiving a hemiarthroplasty for hip fracture versus a total hip replacement for hip fracture at final follow-up. Our outcome is now categorical, not continuous, not numerical, and not normally distributed. There are two groups and no repeated measures. So here we have a choice: the chi-squared test or the Fisher exact test. The chi-squared test estimates the p-value, whereas the Fisher exact test calculates a p-value, well, exactly. Depending on sample size, there may be a particular advantage of one over the other, so check with your statistician. So what if your data isn't actually normally distributed? What if you're not sure? One approach is to plot a histogram and look at the data. Another is to test the data or transform it, but this should be done by qualified personnel only. If your data is not normal, there are usually matching or equivalent type tests to the parametric tests described here. The link shown below goes to an informative page on this issue. I would suggest, though, that if this is where your analysis is heading, that you seek appropriate advice. There's a couple of key points to remember when you're analyzing your data. The first is that the more testing you do, the more likely it is that you'll get a significant result that is in fact due to chance. And this is called a type 1 error. The first protection is philosophical. Stick to your questions and hypotheses, and don't just keep testing until you find something. You heard it here last. The second is to apply a correction factor to your level of significance. This is often necessary in post hoc testing, where multiple comparisons are being done. Ask for advice about A, whether this is necessary, and B, what correction factor is most appropriate for your situation, as there are several options. The second key point is that statistical significance alone may not be enough. Having a clear idea of the MCID at the beginning will help contextualize your results and avoid overselling your conclusions or underpowering your study. If you've arrived here on our loss, don't despair. If you can get to the paired hypothesis point, a statistician will be able to help you get the rest of the way properly. Remember, every statistical test requires a hypothesis relating to the outcome of interest. Hypothesis first, then test, not the other way around. In summary, with a clear hypothesis and understanding of what your data is, you can do a simple statistical analysis correctly. For hypotheses requiring more complex testing, seek advice as you need. In the next podcast, the final installment of the statistical mini-series, Interpreting Your Results.